So today's topic is the filtration and compressed air systems. We will talk a bit about the benefits, the portfolio, and the selection. So what's on the agenda? On the agenda are the benefits. That means benefits for customer and distributors as well. Not so much in detail, but as a general idea how different people think about the benefits in terms of filtration. Next topic will be then the portfolio of filtration. So an overview of the variety of our portfolio. And on the last step, we will have a bit closer look to the selection of filters. There are two different ways to proceed in the selection. We have picked up two different ways. So selection related to process safety or selection based on cost and energy savings. And then we are right at the end of this webinar. Originally, this time will be a bit shorter than the other webinar sessions. Some of you may remember that the others has an extended time of more than 90 minutes, but I can surely promise that this webinar will be a bit shorter than the others. All right, so let's go directly to the first point. What are the benefits of filtration? So from the customer point of view, of course, the customer do not buy filters just because they want to buy filters. Obviously not. They want to manufacture products in high quality. This is particularly important when compressed air comes into contact with products produced. Or they want to keep the production running. You know that downtime is a very cost incentive situation for the customer, and for some processes also a very risky situation. And they want to have process safety because any interruption of production side increases service costs and probably also leads to delayed delivery time and a worse reputation in the market. That could be also a possible result of the interruption in production processes. And what about sales and service people? So the filtration keeps the treatment in good condition. What does that mean? So although in many cases the compressed air system operates under fluctuating conditions, the good filtration keeps or tries to keep the operating conditions more stable and the treatment performance on a higher level. On the other hand, also filtration reduces the risk of emergency actions. Nothing worse than to have an emergency action, because in case of emergency operation, we have stress on both sides, on the customer and at the service technician as well. So there's also a higher risk of failures and accidents during service jobs. So emergency operations or actions should be avoided in best case. So let's have a closer look to the properties and advantages of our filtration series. For that purpose, we have a short look in this cutaway model here that shows the filter housing here on the left, and also a bit upscaled view on the filter element area, which is also cutted here. So what we have is the inner support cylinder, which is made of a mesh stainless steel material. And on the next level, we have the so-called soft pleated material. So what means the soft pleated material? During the manufacturing process of this filter material, there is no pressing of filter material on the edges of this filter element. That means also here in the curves of the pleating areas, here in the inner and the outer area, we have the full filtration volume available without reduction of filter material. Then we have the open support mesh. This is on both sides of the filter element, so on the inner and the outer layer of the filter media, and supports or gives a higher retention against mechanical stresses related to fluctuations in flow, particularly in flow. So we also have the drainage layer, which is responsible or enables the to generate bigger droplets from small aerosols, which has been separated in the filter material. And also this drainage area is being supported by the outer support cylinder. Again here, This is made of meshed stainless steel material. So all these properties of the filter element leads also to a good differential pressure result. We have here again a graph comparing the old version of the filter media, the CLEARPOINT 3E, which is a few years ago has been substituted by the CLEARPOINT 3 Eco, and we have again an increase of energy saving due to lower pressure drop with the new filtration series. But finally, not to forget the filter housing. Also the filter housing is part of the filtration process, and in this case the filter housing is made of corrosion-protected and seawater resistant aluminum. Due to that fact, there is no risk of oxidization, and that also means that the smooth surface, which reduces turbulences and pressure drop, and it has a long-term stability against corrosion, and also because of there is no corrosion, we have also a low risk of particle emission into the compressed air stream. So the low pressure drop is not only, or the pressure drop itself is not only related to the filter element itself, but also in combination with the filter housing. So it also depends on the size. For that, we pick up this graph here that shows different filter element sizes. So we have the S and the M version, so all these threaded filter housings here, but also in different lengths. And the longer the filter element or the filter itself is, the higher is the pressure drop in the same size and in the nominal flow rate. So that is important to know. So probably you could, once you want to increase the energy efficiency, you could select either a longer filter element with a normal flow rate of the smaller size, of the smaller lengths, or if you are here on the edge, you could also select the next bigger filter housing, which has a bigger volume and automatically gives you a lower pressure drop. So in case your customer is energy oriented, that should be considered, that there is always an option to go a bit longer in the housing or switch to the next size, because the flow rates which are allowed in our filter elements has a huge variety. We will come up to that also with a few numbers on the next slides. This factor that you have an increased pressure drop by longer filter elements is also true for any filter suppliers on the market. So as we already talked about, in case of selection process, it depends if you are energy optimized oriented or if you are performance oriented customer. That depends on what type of or what size of filter should be selected. All right. Good. Then I would like to have a closer look on the filter element itself and the different filtration grades we have in our portfolio. And for that purpose, I first pick up the old filter series here, just to show that we originally had 5 filtration grades, C, G, F, S, and N. And some of them has been substituted, and some of them has just become new media for the same filtration grade. So we start with the C filter, the Coarse filter, which has become the CX filter, both in the same filtration grade of 25 micron. This is still the wrapped version element, so there's no pleated version of the C filter element available. All of the Coarse filters are in wrapped versions, but it has the new filter material, which gives a bigger internal volume because of smaller single fibers. That is comparable with let's say with the tree or the forest. If you have a huge forest with a lot of numbers of trees, you have a big volume, and all the particles which are in the air can be collected by the trees in the forest. If you have just one big tree, you have less surface that can adapt all the particles which are transported by the compressed air stream. That's why the new filter element is also more efficiency in all the retention rates. All right, so what happens with the G and F filters? This has been substituted by the FX filter element, and the FX filter element has the filtration grade of 1 micron. And the superfine and nano filter has also been substituted by the SX filter element 0.01 micron. So that means there are no longer G filter elements in our portfolio, and also no longer no N filter, no nano filter elements in our portfolio. This is accepting the nano filter, which is still integrated in the DryPoint M Plus version. But as a single filter, this is not available, and it's not required. We will see that also in some of the next slides. So these two ones, the FX and the SX versions, are our pleated versions of our filter elements. Yeah, in total, you could say that the 3-eco gives you better performance, lower differential pressure, and also less storage space, which is also an advantage not only for us, but also for distributors who requires less space for storage area to be able to deliver all the required different filter grades. What about the filtration performance in total? For this, we compare the old and new filter elements, and we will start with the C and the CX filter element. So the this values has been evaluated by an external laboratory, which has been put in a certain amount of oil aerosols on the inlet of the filter and measured the outlet concentration after the filter element. So from C, we can expect a reduction from 30 milligrams to 5.4 milligrams per cubic meter, and the CX filter element give us a reduction down to 4.8 milligram. In percentage, that's the difference between 82 and 84% aerosol retention rate. When we look at the G and F filters, we end up here at the G filter, the general filter, which is only the old one, down to 0.5, and with the new, with the old F filter element down to 0.12. But with the new FX filter element, with the new filter media, we end up down to 0.05 milligram per cubic meter in oil aerosols. So these are the numbers in percentage. So again, a reasonable change in the oil retention rate. Last but not least, we have the superfine filter series. With the old S, we could go down to 0.04. The nano filter a bit lower because the material itself was not that different, but it was in a more more wrapped rounds the filter. And with the new SX filter element, we could go down to 0.05. And that's the total result in the retention rate in oil aerosol concentration. Easy to identify that we have a almost 10 times higher residual oil content comparing from the old S series to the new SX series. Right. So if you put these single filter elements into a compressed air filter system, we would have a stage filtration, and this result is as following. So that is the result of the typical stage filtration, let's say around the fridge dryer. So we start with the G filter, the F filter, and then we had the S filter before the activated carbon tower, for example. But in the new situation, we have the 3-eco series, which start with the FX because we do not have the G filter anymore. So around the fridge dryer, we would put in an F for the inlet conditions, and again an F for the outlet condition to avoid any particle or water aerosol carryover into the production process. But once there is a carbon tower involved, an additional S filter is strongly recommended, and with the new filter media, we have a 700 times higher oil aerosol separation rate compared to the old ones before. So in case we have, let's say a black pipe system where we have a rusty vessel or pipework included into the system, we would recommend the CX filter before the F filter. And if we then go down to the SX filtration, we still have a 6 times higher oil aerosol retention rate than when compared to the old version. And even if we just put two filters, let's say the FX filter and the SX filter, we still have the same aerosol retention rate, but with just two filter elements instead of three elements in the old series. So again, this result or this combination here gives you also less pressure drop with the same performance as before with one filter more. Right. So important to know also that with the new filter elements or with the actual filter elements, we are also able to run this system with a flow rate between 30 and 100% for the threaded filter housings. For the flange filter housings, this is a bit reduced because the flange filters, the elements are fixed only on their head, but not on the bottom area. So they may get in trouble due to turbulences at higher volume flow. That's the reason why we reduce this flow rate to maximum 110% instead of 130 in the threaded housings. However, the coalescing filters cannot retain oil vapor. So therefore, an additional activated carbon or dust filter is required to achieve quality class 1 in both in particles and oil. And as already mentioned, in case you have coarse particles in the air, an additional CX filter should work as stage filtration process to support the next F filter and to let it run for the regular maintenance period. These performance rates are all evaluated and measured by an external institution, which is called IUTA. This is an institute which is, you could say, nearby our headquarters, and that also certifies the particle retention rate here to see in that table here. So there's a very high efficiency in particle retention with our filter elements as well. All right. So that's so far the topic about benefits of our portfolio. Any questions so far in the chat?
So far, no questions, but maybe we will have some at the next break.
Okay, thanks very much, Mark. We are right at the next topic here, which means portfolio filtration. So we will have a, let's say an overview of our portfolio, of the range of our filtration series. And we will start with the general overview. So what do we have? We have some smaller and bigger filters for the general application processes. And we have also stainless filters for high pressure application and also for sterile application. Some of the key data are mentioned here on the right area. The pressures which can be used are maximum 16 bar or 232 psi for the threaded versions. They can also go up to 50 bar. In case they have the 50 bar version, you have a different thread connection here between head and housing, but from the outside they look totally the same. Then we have the next application gap is the filtration range up to 500 bar, which includes the stainless steel filters. And we also have different maximum flow rates. This is the max flow rate for the threaded housing versions here. And the next flow rate is the maximum rate for the flanged versions shown here on that picture. So how to select now the right filters, and what is the job of the filter elements in general? The reduction of undesirable components, which are particles and aerosols occurring at traffic, industry, and nature. So this is the basic where the compressed air filtration, which is the job of the compressed air filtration components. What products comes into action here? For that purpose, we have a water separator and coalescing filter. So here you could also see the threaded version of our water separator. There's an inlet integrated where we have pedals here that drives the compressed air stream into a circular direction. So you have gravitational forces and circular forces that separates the liquid and water components of the airstream, and then they will be collected on the inner wall and be drained out here. And the air flows back to the inner area out of the filter housing here. And for the other jobs, for aerosols and particle reduction, we still have the coalescing filters here in the wrap version. But also we have flange filter versions. As already mentioned, these filter elements are just put it from the top side of the flange housing. Quite easy to put them in here. Just 2 screws which are fixing the position of the filter element. If you lose these screws, you can turn them counterclockwise, pull them out, and disassemble the filter element from the supporting component, from the thread here. Put a new filter element on here and put the whole combination down to the flange filter. But there's also more than the particles and aerosols which comes from the ambient. Also, the compressors has an influence of the contamination in compressed air itself. And it's no matter if we have the piston type compressors, screw type, or turbo compressors involved here in the process. All of these compressors are responsible to cure particles due to friction. The water vapor and the aerosols and liquids, they will appear due to oversaturation after the aftercooler. And the oil vapor and aerosols will also occur due to high temperatures and the oil carryover in lubricated compressor systems. So considering the oil vapor, this is definitely the most difficult substance to be reduced in the compressed air system. For that, I've picked up one of these numbers here shown in the graph. This graph is to show the different amount of oil vapor comparing to different compressed air temperatures. But we also know that inside the compressor we have higher temperature, so the compression end temperature in degree C is about 80 degrees. In worst conditions, if the compressor room has a pure ventilation, it could easily go up to 100 degrees. And we also have the problem that there is no retention rate of the oil vapor just with the coalescing filters. So that also means the integrated oil separator in the compressor does not reduce the oil vapor content. And even the temperature drop inside the fridge dryer has almost no influence of the oil vapor concentration. So what is then required in terms of oil vapor filtration? For that purpose, we have one option. This is the activated carbon filter. But the activated carbon filter is nothing for continuous oil-free treatment and applications. But it's good for short-term bypass installation or just for very little amount of oil vapor, for example, at the point of use. The main reason for that is the contact zone where the compressed air gets in contact with activated carbon. So that is the small area here. We have first we have a small contact zone and we have a very short contact time of the compressed air stream passing the filter element, which has a small amount of integrated activated carbon inside. This filter is also available in the flange version with the same situation, also as the activated carbon filter. So the real treatment of oil-free application looks definitely different. This is where we come up to the activated carbon cartridge. And the activated carbon cartridge comes in the small versions in the filter housing. So just take the cartridge which has the similar dimension of a regular filter element, and we can simply put in this into the filter housing. And if we look inside, we would see the compressed air stream, which is entering the filter element here on the top, passing the activated carbon cartridge with a very long contact time, and then the reverse flow back to the head of the housing. So inlet and outlet is here on the same level. And for bigger air flows, for large applications, we also have this scenario as an activated carbon tower. Let's once again compare the activated carbon filter with the activated carbon tower. So easy to identify that we have the different contact time here from cartridge to activated carbon filter. And if we take as an example the flow rate of, let's say, 100 cubic meters per hour or 60 cubic feet per minute, then the resulting activated carbon mass of the filter element would just be 22 grams or 0.78 ounce. Comparing to this, the activated carbon cartridge has a more than 10 times higher amount of activated carbon inside. So easy to understand or to realize that that's the real oil-free treatment system, and that is just for, you could say as a police filter at point of use, or for a short-term maintenance period in case you need to maintain another carbon tower or a vacuum cut treatment system. All right. So what else do we have in our portfolio? These are also filters for high pressure and sterile applications. The high pressure filtration rate goes or works from 100 to 500 bar in the stainless steel versions, and from 1450 to 7250 psi. These filter housings are all made of stainless steel, and all the components included also included the caps of the filter elements are made of stainless steel. So that means there's no corrosion and no risk of particle emission from the housing itself. And this is also added with an optional high performance measurement for the pressure drop here, shown on the gauge here. So considering the sterile filtration, we have also both filters in our portfolio. That means the sterile filter itself, but also the steam filter. And although this webinar is not covering the deeper look into these special applications, I would just like to leave a few words about the sterile filtration itself. And if you look on the filter housings, we have different versions available. One is the flange connection, and the two others are the threaded or welded connections. So these are the two design options on the filter housings we have here included. Considering the sterilization process, there are two processes possible. Or three processes are possible, in fact. So on one side we have the so-called direct current sterilization process, and on the other hand we have the counterflow sterilization. So what is the difference in that purpose? The difference is the airflow, the internal airflow in this sterile filter housing. The counterflow sterilization is usually only used when the steam is also used for any application process. So in case that's the scenario, then this installation would be set up as shown here. And once the element should be sterilized, these valves will be both closed here, and then the steam valve is still open and flushes or purges the element with a lot of mass of hot steam. And the steam will be escaping the filter housing. either on top or bottom, depending on if this process is running or this process is running. So on the left side, we have the direct current sterilization. That means the steam follows the same way as the compressed air. So it follows the filter element from the inside, and the steam flushes the collected bacteria out of the filter element, and the steam will also leave the filter housing at the housing itself. But this sterilization process is only possible if there is any steam application on site, or if there is steam anyhow available at this customer on site. Another option is that the sterilization can be done in a so-called autoclave, but for that purpose the filter element needs to be taken away from the filter housing and put into the autoclave for the sterilization process. And then again, the filter element needs to be placed in back again to the sterile filter housing. All right. So that was the quick overview of the portfolio so far. Any questions in the chat?
No questions.
Yeah, probably it's because of we are talking just about filters, which is not so big topic, but we will see that they are definitely important for good running processes and for process safety. So let's go ahead with the next slides here. We will deal now with the topic of selection of filters, and in the first step I would like to have a closer look to selection related to process safety and the application. For that, let's say exercise, I prepared let's say an installation that shows the regular treatment process down to an oil-free application. So we have the compressor, the receiver with a drain integrated, then we have the desiccant dryer, we have the activated carbon tower, and this all ends up to an oil-free quality of class 121. So question now is for sure where to place all the filter elements. Of course, at first we should integrate the water separator to get rid of any liquids and droplets which come from the compressor after the aftercooler. Then we start the stage filtration to prepare best inlet conditions into the desiccant dryer. And for that purpose, we put in CLEARPOINT F with a 1 micron filtration grade. And on the next step, we put in a CLEARPOINT S with an 0.01 micron filtration grade. So we have best conditions for the desiccant dryer, particularly in terms of oil aerosols. This is that's the reason why we put in the S filter before the desiccant dryer. So finally, we place the dust filter on the way down to the application to avoid any carryover of dust particles and to keep the compressed air in a good quality to be used at the production process. But finally, I would say not to forget an additional dust filter between the desiccant dryer and the carbon tower. Remember that we talk about process safety, which is here the priority, and any abbreviation inside the desiccant bed, inside the desiccant beads, will create dust, and if there's no dust filter in between here, all the dust will be collected on your activated carbon, which also results in, it also gives two results. It reduces the active surface of the activated carbon, and it will also increase the pressure drop for the air which is passing through that tower. So it would be definitely more easy to exchange the loaded dust filter than to exchange the activated carbon, just because the pressure drop has been occurred. So that's the one example for the oil-free treatment. Another example with the next installation, this comes up with two different quality classes on the way to production. Again, here we have the receiver. Now we have the fridge dryer with the integrated drain here, and we have an activated carbon. So the way the compressed air flows from the the fridge dryer directly to the application is with the quality class given in 242. And the oil-free application for sure requires a higher quality with less amount of particles. But in oil, we would not be able to achieve class 1 here, not in the given situation with the integrated fridge dryer in that combination here. So the same question here, what filters should be integrated? Of course, the water separator for the same purpose as before. And then on the next step, we would integrate the F filter 1 micron to prepare the compressed air in good conditions to run through the fridge dryer. Then the next filtration grade is selected due to the oil-free treatment with the carbon tower. Also again, particularly in terms of oil aerosols. So that's the reason why we placed in here an S filter instead of an additional F filter, as we would use for the regular application for 2.242. But because this air also is being conveyed to the carbon tower, we have decided to put in an S filter here. And finally, this S filter, the side effect of this S filter is also that we have a lower particle emission down to the application here for the workshop area. And finally, of course, a dust filter should be integrated as well here to avoid the particle carryover into the application process. What else is worth to be mentioned? That is the filter, the upstream filter for the activated carbon tower. So you could generally say that upstream filters, which means the filters which are preparing good inlet conditions, these should be placed as close as possible to the next treatment process. And this is particularly important in this installation here, where we just run the fridge dryer upstream the activated carbon tower. Let's assume that the carbon tower is installed a bit more far away. So maybe because of the situation on site, it needs to be placed in a different room. So it's several meters away from the fridge dryer. Or let's assume the vessel or the receiver is placed in between the fridge dryer and the carbon tower. In that scenario, you have a long distance between the fridge dryer and the activated carbon tower. And in longer pipe systems, there is always the risk that additional oil aerosols will occur on the way from the fridge dryer down to the activated carbon. And if you put this filter, this S filter close to the fridge dryer, you have a long distance between the filter and the carbon tower with a higher risk of additional aerosols occurring on the way to the carbon tower. So the recommendation is always to place this inlet filter for the carbon tower directly for the carbon tower itself to minimize the risk of oil aerosol concentration into the carbon tower. Some of you may remember the topic of the oil-free session from some of the other webinars, that oil-free adsorption or oil vapor adsorption is a very sensitive process, and we should consider that we always prepare best inlet conditions for our carbon tower. All right. So last but not least, the last exercise here. And this exercise is a bit different to the others because we have first here a central treatment area at the compressor station with a fridge dryer that delivers the so-called workshop air in class 242. And we have an additional point of use area where an extra treatment is required because this application requires a quality in 1:1. So again, we start here also with the water separator for the purpose of reduction of liquids and any aerosols. And again, here we put the F filter into the fridge dryer at the inlet and also at the outlet, because that's the central treatment situation or installation at the compressor room. And this scenario is good for our workshop area. It's not required that we consider any further treatment at point of use, because here at point of use we will prepare this treatment process with a separate filtration unit. Also because the size is definitely different here compared to this area here. Because this filter, or this fridge dryer and all the filters integrated here needs to cover the full flow rate of both applications from the workshop area and for the oil-free area. But this treatment process also needs to cover the smaller amount of airflow for this purpose here. So how to start here at the compact desiccant dryer? We would definitely, of course, put in an additional S filtration, a coalescing filter with the 0.01 micron filtration grade. And the required quality class 1 in oil requires an activated carbon cartridge, which can be placed directly after the desiccant dryer. This can be integrated directly here because the compact desiccant dryers has an integrated dust filter in their internal cartridges. So there is no dust filter required in between the CLEARPOINT V and the compact desiccant dryer in that scenario. But of course, we need an additional dust filter to avoid any particle carryover into the sensitive application over here. All right. So that's so far the selection in terms of process safety. Are there any questions occurred in the chat room?
Yeah, there's a question. Did you say that fridge dryer doesn't reduce the oil vapor amount? Because the attendee thought that oil vapor amount should be reduced in fridge dryers because it reduces the compressed air temperature up to 3 degrees Celsius.
Yes, I think I know what's the question. The point is that the temperature reduction works perfectly for water vapor reduction. That means the water vapor can easily be condensed inside the fridge dryer. But the time to transfer oil vapor into oil condensate, or let's say into liquid oil, is far longer than the time which is required for water vapor into water condensate. So that's the reason why the fridge dryer has just a little influence on the oil vapor carryover into the downstream system.
And there is something question. There is a question: do we oversize these filters with so many inferiors in an effort to minimize the overall pressure drop of the system?
Yeah. Okay. I mean, I understand. So that, of course, if you put in a lot of filters into the system, we will definitely increase pressure drop. That, of course, is for sure. But the first priority is always process safety, and to keep the treatment system continuously running in good condition, there's no question about filtration. So we cannot run the risk by reduction of amount of filters just to save some pressure drop, but there's still the risk that we have a poor long-term stability of our treatment process. And that's, I mean, of course, it depends on the focus of the customer, but from our point of view, we will always recommend to create best performance conditions of the treatment system. And of course, we pay for that with an extra pressure drop with each additional filter.
So there's a comment, yes, but is each one maybe the next size larger?
I have no idea what's mentioned with that comment. I mean, if we go each size larger, we would run the risk that the velocity of the filter, the velocity of the compressed air stream gets lower and lower. And the more critical situation for the filter element is a too small velocity. Yeah, it's from the performance point of view, it's more easy for the filter element if you run an overload in flow rate than in a lower flow rate. Of course, we would win some pressure drop if we would install a bigger size of filter. But of course, any bigger size of filter is a higher number in price, not only for the filter housing, but also for the filter element. So finally, it's a complex calculation for the overall running costs. We will also come a bit to that point on some of the next slides, and I would not recommend to put bigger sizes just to reduce the pressure drop, because the disadvantages, I think they pay more. The disadvantage is you may need reduction fittings. Any reduction fitting is also needs space and has a potential of leakages, and so on and so on. So I would stay for the same size, yeah, if you have the required airflow to treat. Yeah, I mean, it's not easy to answer that question, because there's always the question, or then the requirement to run the system with the lowest pressure drop possible. But on the other hand, we also need definitely process safety, which is in many cases the most critical point for the customer.
So to absolutely guarantee class 1, would you recommend a sterile filter at the final stage? Because sometimes we find that when we test the compressed air, we cannot always achieve class 1 without sterile filtration.
So is that related to particles? Or I guess, so far as I understood, it's related to particles.
Yep, I think so.
Oh, okay. Good point. I've never heard about that. If that's an experience from the market, yeah, it would be good to be discussed. But honestly, I have no idea what would be the pressure drop in the sterile filter element in a regular maintenance period of half a year or 1 year. I can assume that this is totally different to our regular coalescing filter elements. But if that was the only way to achieve class 1 in terms of particles, then that might be a solution, although it's a very, very cost intensive, because the sterile filtration package, this includes the stainless steel filter housing and the stainless steel filter elements. But honestly, I have no idea about that experience, and yeah, it would be good if you could pick up that discussion in a later session again. Thanks for that comment as well.
Okay, this is all we have right now, so you can go ahead with your presentation.
Okay, thanks very much, Mark. Right, so let's have a look on the next point, where we would select filters based on cost and energy savings. For that purpose, we have picked up that scenario which we have seen before, and the filtration grades, they have already been set, and we have additionally got a few numbers from the application from the customer. So we have the current situation that we have an operating pressure of 8 bar or 116 psi. We have a compressed air temperature of 35 degrees Celsius or 95 Fahrenheit. And we have a flow rate of 720 cubic meters an hour or 423 cubic feet a minute. So obviously we have some calculation required, because the operating pressure is 1 bar above the standard system pressure of 7 bar. That means with the current system pressure, we need to calculate the original given normal volume flow. For that purpose, we take the numbers from the price book. Here the table sheet. And we will find the correction factor for pressure, operating pressure of 8 bar, or the 116 psi, and calculating the volume flow with the correction factor, we will end up at these two numbers here, the 673 cubic meters per hour or the 395 cubic feet a minute. So the matching flow rates on the table above are shown here. So we either have the 780 cubic an hour or 460 cubic feet a minute, and can select the performance-oriented MO20, or we can here, with the same flow rates, can select the energy-optimized filter size MO22. These two filters have individual pressure drop. So the one is given here with 180 millibar or 2.61 psi, and the bigger size have with the same volume flow from the customer. It has 150 millibar or 2.18 psi. That results in a potential or in a saving potential of 30 millibar. But what does that mean in saving potential per year? For that calculation, we also need to have a look on the compressor itself, and we assume at this flow rate we have a 85 kilowatt compressor. And we also know that in average, 1 bar or 14.5 psi increasing of pressure will end up in an energy consumption of an additional energy consumption of 8% from the compressor installation. So this calculation with 30 millibar or 0.435 psi will end to an energy consumption increase by the compressors of 0.2%. And using that 0.24% for the kilowatt calculation, we will end up here at 0.204 kilowatt hours on a higher energy consumption rate for the compressor itself. So what does that mean in euro per year? For that purpose, we take the 0.204 kilowatt hours, multiply that with the operating hours, which are assumed by 5,000 in that case, and we put an average price for the electricity in the industry with a 15 euro cent. So this ends up to 153 euros extra because of the 30 millibar differential pressure. Or let's say that's the saving potential if we would go for the energy optimized filter size. But we also need to consider that the larger filter element costs an extra 70 euros. So in fact, that means these 70 euros needs to be subtracted from the 153. And the real energy saving, or the real money saving potential is the 83 euros, which results in a 166 euro savings per year if we would go for MO22 size with 2F grade filtration. You may remember that we had in an exercise before that we had activated carbon tower after the fridge dryer, and in that case, if we put in an activated carbon, we need an additional or a different filter after the fridge dryer, and for that purpose, we switch over to this scenario here. And here we have the activated carbon tower after the fridge dryer. That means the filter between fridge dryer and carbon tower should be an S filtration, so an 0.01 micron filter. And then we have a slightly different base where the calculation should start from. At first, the pressure drop here changes from 180 to 210 millibar, or the corresponding 3.05 psi. And the same situation we have here. that the pressure drop will increase from 150 to 170 or from 2.18 to 2.47 psi. So these are the individual pressure drops from the filter grades, and comparing to these, we have an extra 10 millibar. That means we have 40 millibar differential pressure between the both solutions, or 0.58 psi between these two different sizes. Coming back to the calculation with the compressor, we will end up to 0.32% of increased energy consumption of the compressor, which will end up to 0.272 kilowatt hours in energy consumption in total. So per year, this calculation ends up to 204 euros. And if we now combine the 1F filter, that's the energy consumption of 1F filter, that's the energy consumption of the 1S filter, we have a saving potential of 214, which is not the same as 24 plus 153, because here the extra price for the bigger filter amount is already included. So the 240 euro savings per year, yeah, that doesn't sound very much, but related to the consumed kilowatt hours, this is approximately 1/3 of the yearly electricity consumption of a household. And if you get that picture, yeah, 1/3 of energy consumption of a household is this saving potential if we just change from performance-oriented to energy-optimized. Maybe this is worth to be considered, but finally, it definitely depends on the type of customer we are talking to. Yeah, that leads to almost the last slide. What else counts for the right selection of filtration system? So how to make the right choice in filtration? That depends, in fact, on the type of customer. So whether he is a quality-driven customer or he's focused on invest, on running cost, or on process safety. It furthermore depends on the application requirements. So what quality classes need to be achieved? Yeah, do I have a central purification process, a point of use, which components are involved? And of course, it depends on the compressed air treatment process itself. So as shown in the example before, it's a different scenario if I have a carbon tower, which needs to be prepared with an S filter, or if I have just a regular treatment process for a workshop area. So these are some of the topics that might be to be considered when making the right choice in filtration processes. That's all for now, and at my point of view, it's time to say thanks for your attention, and I'm very happy to see you next time. And if there are any questions in the chat room, just let me know right now.
There are at the moment no further questions. Yeah, thank you once again for joining our webinar. Bye-bye and enjoy your day.